Okay, welcome to the 43rd lecture. What we have been discussing about earlier, it is the spin stabilization. Now, we enter into the reaction wheels and control moment gyros. So, reaction wheels and control moment gyros, they are used to control the attitude of the satellite, but before we enter into that topic, so we will have some video for that, and we have a problem here also, that the problem is like we have a top, say that plate top. Okay. So, this plate top is hinged over this point. So, this point is a ball socket joint. So, this gives it 3 degree of freedom. Okay. Now, this cone is rotating on its axis. Basically, this is the spin here, the spinning. Okay. This phi dot is the spin rate, and psi dot, this is your the precession rate, and theta dot we will call as the nutation rate. Already we have discussed this thing, the rigid body dynamics. Okay. So, we will do this problem. So, this will expose you to how the rigid body dynamics problem can be solved. Okay. Now, here in this case, the as you know, once you play with the top, so it is spinning at some spin rate which is given by this phi dot. Okay. And it makes certain angle with the vertical. So, this vertical I have shown it here in this place. Okay. So, this is your vertical fixed axis. Okay. And the gravitational torque, it is acting here. Okay. So, x and y here shown, x, y, and this is a small z. This is small z. So, this is capital Z, there is a difference. So, x, y, z, capital X, y and z, this constitutes inertial frame, while the x, y, z, small z, it constitutes the body frame. Okay. So, here this is fixed to the body. So, x, y, z, this is fixed at the body frame, fixed at the center of mass of the cone, but not spinning along with the cone. Okay. So, why we are not fixing, you will see later on what is the advantage of not fixing it. We can also fix the body axis such that it is a fixed here, and thereafter it is rotating along with the cone as shown in this direction. This is the anti-clockwise as seen from the top. Okay. So, this is the rotation here. Okay. Now, we have to solve certain problem related to this, which I am going to state later on. Okay. So, here the torque acting is about the y axis. This y axis here, it seems to be, this is coming out here, we can maybe we will change it little bit, the y axis. Y axis we can show like this. So, this is your y axis. So, the gravity x axis is inclined like this, what it has been shown here. So, x axis is making theta angle, because this is this particular line, the axial line of the cone, it has got inclined with this vertical line by theta degree here. So, this x axis will also get inclined with the horizontal by theta angle. So, this will be theta angle, which I am not going to show here, because this will unnecessarily complicate the figure. Okay, we will take up this issue later on also. So, here basically due to the gravity, there is a moment about the y axis, okay. And under this moment. So, this is not a torque free case. Earlier if you remember in the rigid body dynamics, we have taken the case of a cylinder, okay, which is precessing and there is the nutation angle involved and it is spinning phi dot here, this is theta, and then there is the psi dot is present. Okay. But that case we have taken where it was free from torque free rigid body dynamics we have done, free from. But here in this case it is not free from torque, there is a torque acting at the center of there is a force acting at the center of gravity, and therefore, a torque will act along the y direction. If we put here x and y are shown here, okay, if I push it here to the bottom point. So, you will see that along the y direction the torque is acting. Okay. So, let us look into this video. This is from the YouTube. If you see here this particular line, this is the equatorial plane, the green plane which is shown, it is equatorial plane, and the dotted line here. Okay, so, here this the dotted line, it is your it is called the ecliptic plane. Okay, already we have discussed about this just in the beginning, and the green line which is shown here, this is the equatorial plane. You are seeing from the equatorial plane from the side, and this is a view of the ecliptic plane from the top. So, see now you can see that the ecliptic plane and the equatorial plane, they are cutting along this line which is shown by the red line here. Okay. This is the, you can see the cursor, it is moving. So, this is along the red line, this is called the line of nodes. Okay. So, here in this case what is happening, that as this is the earth, okay, and earth equatorial plane, it cuts the ecliptic plane and it cuts along this nodal line, okay, and earth is precessing. So, if you see the let us go further and see, you can see that this axis which is shown here, this axis it is rotating about this vertical line. Okay. So, this motion is the motion that takes place like this, as you see by cursor. So, this line this motion it constitutes the precession motion. Okay. So, this is see the small this dotted line is getting generated here. So, this is the precession. Okay. And your line of nodes which is shown here by the red line, it is rotating. So, this rotation it takes place nearly around 25,800 years, means 26,000 years roughly you can say, it goes through 360 degree. Okay. So, that means in 26,000 years this line which is moving here, it will go once round like this. So, right now this line where I have put the cursor. Okay. So, about this curve where the circle has appeared. So, this line right now it points toward the Polaris, okay, what you call as the pole star. Okay. After 5,000 years there will be no pole star for the earth. Okay. Right now the axis of the earth about which it is rotating. So, that is pointing toward the Polaris. Okay. So, and thereby it is describing a circle like so. This is the precession motion. In addition, there is a small nutation motion which is not visible here, that takes place about the green line itself. You can see that I am showing it by cursor, it does like this. See the cursor, it is moving like this. So, it will do this kind of motion. Okay. So, this is called the nutation motion. So, the axis, the angle between the earth axis and this line and this earth axis, it is a 23.5 degree roughly. And because of the nutation its average value. So, because of the nutation it keeps changing, okay, it keeps oscillating about 23.5. Okay. And this is the north pole of the earth. So, now if we it is showing here that at what time where this the this polar axis will be pointing. Okay. So, and this Cancer and other things. So, what has been shown here? So, it is showing the this line of nodes as it is moving. So, sometimes it will be in the constellation of Aries, sometimes in the constellation of Cancer and so on. So, there are overall how many constellations are there? As you know from your astronomy part or the even in the astrology part, this is quite well known. This is the total 12 constellation, we call it Libra, Cancer, Scorpio and so on, Pisces. So, your nodal line will be along the different constellation during different period of time. Okay. So, what my objective here is to show you that even this earth, okay. So, this precesses and this nutates also, okay. And as a result it is a polar axis. Right now it is toward the Polaris, as we know our polar star is the Polaris, and it will keep changing over the period of time. Okay. So, why does this happen? This happens because of the torque acting about the center of gravity of the or center of mass of the earth. Okay. About the center of mass of the earth there is a torque acting, and that torque is responsible for your this precession motion. Okay. Let us see another video.
Wheel and axle spin freely, secured in a metal frame. This simple device can
there
behave
is
in the most
simply
unexpected
wheel is
ways.
rotating about this axis where the cursor is there. Okay. About this axis the wheel is rotating. Okay. So, if you spin the wheel at a very high speed, so this is equivalent to a disc rotating about this axis. Okay. Now, if we do this thing on the earth, so we cannot make it free from the gravity. Okay. The torque will be acting on the system, and because of this torque the system will precess and this will nutate. So, this I am going to show you through the mathematics. So, this will be a problem that we will be doing it completely. Okay. So, let us look into this video. So, how the system it works. Here the spin stabilization concept also comes into picture.
Try to stand it on end and it falls over.
Okay. See this normally if the wheel is not rotating, if you keep it like this, so it will simply fall.
Apparently
okay,
it
it's a
can't
falling.
defy gravity. But spin the wheel and
Okay,
all
but
that
if you rotate the wheel, then it is spinning about certain axis. Okay, and there is the angular momentum associated with this, and wheel tries to maintain that particular direction until unless disturbed from that. So, here in this case the gravitational torque will be acting, and that will tend to disturb it, and therefore, as a result of that it precesses and nutates. Okay. So, you will see shortly in this video that you can look through such videos. Okay, you can see that it is maintaining this direction. Earlier it was not able to stand, but now it is standing up, and this and once the velocity of the wheel, the angular velocity of this wheel it becomes small. So, thereafter it will come down.
Incredibly, this force will support the gyroscope like this.
Now, you see the earlier it was not standing there, now it is standing and it is rotating. Okay. It is a precessing, okay, and there is certain nutation angle involved with this. So, this happens because it is having certain amount of angular momentum, okay, and this we have used for the spin stabilization of the satellite. Okay. So, by spinning any object you can make it point along certain direction, okay, and if you perturb from that direction, okay, then it will tend to rotate. You can see again. Okay, so, this is undergoing precession motion, and there is the associated
this interesting behavior
nutation angle also. Okay, so, we stop here with this video. Okay, so, this cone simulates that gyroscope what we have seen, okay, and it is rotating about this point. Okay, this is the ball socket joint, and it is spinning about this axis. Okay. So, derive the equation of motion for this, analyze how much will be the angle and other things. So, as I am going to state it on the next page. So, problem is to derive the equation of motion for the gyroscope So, we state here the following problems. This is capital Z and this is a small z. Okay. There are two axes we have already shown. This is capital Z here, okay, and the small z is shown here in this place. So, observing that E m z and about the vertical axis and about the central axis of the body, about this axis there is no torque, because the whatever the gravity is acting. So, torque due to this it will arise along the y axis. Okay. And similarly, along this axis there will not be any torque. Okay. Though it is a processing along this, you can see the gravity is acting downward. So, in no way the corresponding torque can be along this direction. So, therefore, these two conditions are satisfied. Let be the moments of inertia of the top about its axis of symmetry. So, this is associated with the small z axis and these are associated with x y axis. So, these two are, if this is along z, so this is along the respective transverse axis which is x and y. So, derive there is some change of symbol we will do here. Because the symbols we have used phi dot for the spin. So, the same symbol I will continue with, I will not use a new symbol. this is psi dot and this will write as phi dot and this also as the phi dot. So, these are the two first order differential equation that you need to work out. Use the above equations to show that rectangular components omega small z it is written. Okay. Angular velocity of the top is constant so omega z of the angular velocity of the top is constant and that the rate of precession also we can it can be shown that plus so that this rate of nutation this can be written as a function of theta so these are the objectives that we need to fulfill. So, already we have discussed about the rigid body dynamics of a torque free motion. Okay. Here let us consider that there is a hoop like this or a square hoop which can rotate on this axis and this we write as rotation rate as psi dot. Okay. And in this direction I will write here capital Z. Then let us take another frame which is here attached to this. So, this is on the gimbal. Okay. So, it can rotate here, there is a bearing here. Similarly, the bearing is here. So, I will not write here bearing because I want to tag it with the corresponding directions. And thereafter, there is another bearing here to which to a wheel is attached So, this is bearing here. So, what we have discussed earlier about the top, it simulates the this gyroscope, it simulates the same motion. How? This frame, this is the outer frame, we assume this to be massless. Okay, so, the associated moment of inertia will not be present. Similarly, this hoop also we assume it to be massless, and therefore, associated moment of inertia will not be present. This is having mass, and it is rotating about this axis. Okay. Now, consider this in a different shape. So, we have say this the outer body, the outer frame, it has rotated to some other orientation, okay, which I am showing here. So, this has rotated here, okay, and the rotation angle, the corresponding rotation angle we can measure. Okay. So, let us say that if I measure the rotation angle from right now this is straight. Okay. So, z we have shown here and x and y we can show. Okay. So, let us say this direction is x and y is somewhere, or either we can do it in a little better way. So, first of all, let us just look into the figure that it is rotating. So, let us say that the frame has rotated by angle psi. We are not worried about from which axis. So, this is the axis here. So, initially this frame was coinciding with this line. Now, it has rotated by psi angle here. Okay. Then thereafter, we assume that this red frame, okay, which is shown in the red. So, this red frame also this has rotated. Okay. So, this is the bearing here about which it rotates, and as a result it comes out. Okay. So, this rotation we can show it like this. Okay, it is a coming out. So, now it has got inclined. Okay. So, if I see it from the side, if I look from this side, so it appears like this. You have this frame, if you look this frame from the side, it will appear as a straight line, okay, and the red frame it will appear inclined like this. It will appear inclined in this way, and this angle we show it by theta, that it has rotated by theta. Okay. If you look at this frame, if I see it from the top, okay, here as it is shown. So, from the top, so this frame from the top, it will also look like a straight line. Okay. And if I rotate it by psi angle, so this is going to look like this. Okay. It has rotated by psi angle here. Okay. So, this rotation is like this, if seeing it from the top. Okay. So, this is rotating anti-clockwise. Similarly, this has rotated like this, and inside this then your wheel is there, the wheel that is rotating. So, you have a wheel here which is mounted on this axis, and this wheel is rotating. So, this rotation is here given by phi dot. Okay. This rotation you are showing it by psi dot, and the rotation which has taken place here, this you are showing by theta dot, because this angle has changed from this place to this place, and therefore, this is psi dot. Okay. As you can see, like this is rotating like this. So, this is giving rise to the psi dot. Okay. Similarly, the theta dot, it is appearing like this. So, along the thumb direction, theta dot will be appearing. Okay. So, this is the anti-clockwise motion shown here. So, this is anti-clockwise motion. So, all the motion I have shown, this is the anti-clockwise motion. Now, we are ready to discuss about the gyroscope, what we have formulated. So, we will continue in the next lecture. Thank you very much.